Okay, so now I want to talk about something called a warping path, which is a way that we can match two time-ordered point clouds which follow similar paths but may do so at different rates. So these two figure eights, they kind of trace the same parts. I mean, they're a little bit different, but overall they do the same thing. The main difference between them is that the blue one is much slower at the beginning. We have a lot more samples at the beginning, and then it slowly starts to speed up more and more. So we have fewer samples in between towards the end. So what that translates to in a cross-similarity matrix is we see that we get this kind of elongated bright region where they're similar. So over an interval of about 50 points, I'm similar to an interval of only 20 points along the first curve. Okay, so it takes like 50 points to travel basically the same amount that I traveled in 20 points on the second curve. Now we can match these two together with this thing called a warping path. And there's a few different ways to understand this. But let me just compute it first and I'll plot it. So I actually created a library called linmdtw. It stands for Linear Memory Dynamic Time Warping. You can install it with pip install linmdtw. So it'll do that. Anyway, but you're going to actually implement not as fast a version as mine, but a vanilla version in class that does this. But we'll take it as a given for now before I explain how it works and just see what a warping path actually is. So if I say, in addition to computing the cross-similarity matrix, I say path equals linmdtw dot linmdtw y1, y2, I get this thing called a warping path. So let me plot this both on the left and... Alright, here are two different ways to look at the warping path. One of them is as a path from the upper left of the cross-similarity matrix to the lower right of the cross-similarity matrix. And the warping path that I chose here happens to minimize the sum of all of the distances that it passes through in this cross-similarity matrix. You could draw many paths here, but this is optimal in the sense that it minimizes the sum of the distances. Okay. Another way to look at it is actually every point on this warping path gives me a correspondence between a point in the first point cloud and a point in the second point cloud. So I look at this point here. It's at row 20, column 50. So that means the 20th point on the first point cloud, probably somewhere around here, corresponds to the 50th point on the second point cloud. So you can draw these little line segments between. So it really shows a matching between the two. So a matching that occurs in sequence. So I've colored these, dark at the beginning, light at the end of this matching. So the matching occurs in order. So let me just rigorously define the rules of what warping paths I can create. So a warping path is a sequence of correspondences ij between a point I in the first point cloud and a point j in the second point cloud, satisfying the following properties. So, number one, the first pair is 0, 0. So in other words, we always match the first point in the first point cloud to the first point in the second point cloud. Okay. The second rule is similar. The last pair is n-1, n-1. So we also match the last points. So we start at the beginning and we end at the end. But then the question is, what are we allowed to do in the middle? So let pi equals ij be the, well, let me say, I guess I'll say pk. Use a different letter here. Let that be the kth correspondence in the warping path in a sequence 1, to dot 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 k dot 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 up to, I guess we'll say, I don't know, capital P for P total points in the warping path, or for P total correspondences in the warping path. Okay, then there are rules about what the next one can be. So there are restrictions on what the next one, P of k plus 1, can be. So it can be the following three options. So it can be I plus 1j. So I move forward along the first point cloud but stay still. So move forward along the first point cloud but stay still on the second one. I can also have ij plus 1, which is move forward along the second point cloud but stay still on the first one. Or I could move forward by one step along both of them. Okay, so notice I can at most move one step. I can't move more than one step. So those are the rules. Okay. Let me see if this formats this better. There we go. Okay. So if I'm at a point ij, to walk to the next one, I can either move forward along the first one only, move forward by one step along the second one only, or move forward along both by one step. So if I look at this, I see, okay, at the beginning here, I happen to stay still along the first one and move a bunch along the second one. So that's the second case here. And I keep doing that. Okay, now I move forward along both, but I stay still on this one for a little while as this one catches up. Okay, now I move forward along both again, stay still for a little while as this one catches up. Eventually, the opposite thing should start happening. So now towards the end, I should stay still along the second one and move forward along the first one. And towards the middle here, you see that they both move forward at the same rate. Okay, so those are the three cases that can happen. So I'm not allowed to jump forward by more than a step. But the other thing is I do have to move forward. Okay. So in my algorithms class, I had a little animation which I'll link to, but let me just go there real quick. If you want to learn more information about this, I'll provide some links. But I made an animation of kind of all possible warping paths. And there are many possible warping paths. But even just for a simple example of these two time-ordered point clouds, here are all the possible warping paths you can have. Here's visualizing them in a cross-similarity matrix. And on the right, it's showing them between the two time-ordered point clouds. So you can see you always have to move right and down. That's the rules. So J has to be strictly non-decreasing and I has to be strictly non-decreasing. So they always kind of move to the right and down. And what's interesting is there are many, many ways to do that. So if I'm matching, here's a table that shows like what are the number of possible warping paths between a time-ordered point cloud with 8 points and another time-ordered point cloud with 8 points. And that's not very many points, right? But we see almost 1 million possible warping paths. So we're going to have to figure out some way to narrow these down a little bit. There are many possible paths. Almost exponentially many, asymptotically. So we're going to talk about efficient algorithms to compute these. And LinMDTW, that library I told you about, has some very efficient algorithms. Certainly we should want to do better than checking all possible warping paths and seeing which one minimizes the sum along them. But for now, we'll take it as a given. I'll explain something in a moment that will get us warmed up for class. But I just want to look at one more example with audio this time. Okay. So let's think about audio. So let me load in these two little tunes. So there are two different performances of Vivaldi's Spring. And if I just line them up, one in the left ear, one in the right ear, you get this. So if I were the conductor and that was my orchestra, I would not be very happy, okay? Those do not line up very well. So post-processing, can I make these two things line up? Well, yeah, I can use this framework and I can try to find a warping path between the two. So I've written some code here which will actually apply the warping path by stretching the audio. We'll talk a little more about how this works in a few weeks when we talk about an auto tuner. But for now, I've done some time map stretching. So I'll be able to actually stretch the audio so that I'll speed it up and slow it down so that it actually, things that match in the warping path actually will be played next to each other. So that would amount to, you know, if I were thinking about these two as like tunes, that would amount to slowing down the red one here and then speeding up the red one here. So you could think about it that way. But so how do we cast this problem of audio into this geometric framework with a cross-similarity matrix? Well, so we can compute the MFCC features. Now the MFCC, if you remember, they come back usually, you think about it, it's kind of like a spectrogram, where each column is a window, and the rows correspond to the features, or the frequencies if it's a spectrogram. We're going to want to keep it in this framework where we had, you know, we actually had the time axis down the rows and the dimensions were along the columns. We're going to have to do something called a transpose. So we actually want to put each window along each row. So we're doing something called a transpose, which flips the rows and the columns. So that each window is along a row. And the MFCC has 20 different numbers associated to it. Actually, you can choose even fewer if you want, but 20 is one of the standard numbers of dimensions in MFCC. So you can think of, actually, when you summarize a tune this way, each window can be thought of as a point in 20-dimensional space, which is a little bit abstract. But the cool thing is you can use this you know, the distance measure that we talked about. This totally applies to points in 20-dimensional space. So I will loop through every dimension. I will loop through every column in my window, and I will take this square difference between that column, sum all of them up, and then that will give me a distance between 2 points. Okay, so I can compute distances just the same way. So let me go ahead and do that. So I can make a cross-similarity matrix, and I will then also show, here's the warping path. Okay, so here's what the cross-similarity matrix looks like. Actually, if you remember, if I go back and play the original audio, one of them started before the other one, so you can see actually, you can see this kind of lag here. Actually, I guess they both took a second to start, but one of them started even later. So there's one of them that we get this kind of vertical region here where one of them's not even playing at all yet, the other one is playing. Okay, then they match up like this here. There's a little bit of warping in the middle. Let's listen to hear what this sounds like. Not bad. Okay, cool. So that seems to have done it. All right, so I want you to do an exercise real quick where you just compute what is the sum of all the distances through the cross-similarity matrix along some given warping path. And then I just want to talk about something that we'll work on more in class, but how do we, I want to talk about some of the steps of how we actually compute an optimal warping path. Like, this is a good one. This happens to minimize the sums of the energies through it, and we get a good lineup between the two. But how do we compute this efficiently without checking all these exponentially many paths? That's going to be the question. Oh, and one last important thing I forgot to mention. Just like when the distances were small here, it meant that these things were close to each other. We can also think geometrically that a small distance here, it means that two windows are close to each other. So what it means is these two windows are capturing similar audio if their distance is small. So that's the interpretation. So we want to find a bunch of windows in sequence that are very similar, even if it takes one of them a little bit longer to have similar audio content. We want to match that up. Okay. So the idea is small distance means similar audio. Large distance means different audio. So we want to find a bunch of similar audio clips in sequence. Okay, cool.